In this question, we will address how to find the equivalent capacitance of circuits. Furthermore, we will describe how the properties of capacitors in parallel and those of capacitors in series differ. In a circuit, capacitors can either be in series or in parallel. First, we will discuss capacitors in series.
Let's assume that all capacitors were uncharged at one point in time. When voltage is first applied to capacitor B, giving the right side of B a negative charge, that same current will flow through all the capacitors. Since one side of capacitor B has a negative Q charge, then the other side of capacitor B will have a more positive Q charge. Electrons are carried from capacitor B to capacitor A, which means that the charge stored by capacitor A must have come from the capacitor B plate. The electrons were transferred through all the capacitors, which is the reason that the charges at each capacitor are equal.
For a circuit with capacitors in parallel, the charge could flow through either the path which crosses capacitor A or the path which crosses capacitor B. Therefore, the sum of the charges across both capacitors equals the total charge which passes from the input wire to the output wire. Since the capacitors A and B are connected to the same input and output wires, the potential differences across the two capacitors are the same, so delta V of A equals delta V of B.
In a given circuit, there may be a mixture of capacitors in either series, parallel, or neither. To get the value of equivalent capacitance of the whole circuit, the capacitors can be combined for simplification. The manner in which they are combined depends on whether they are in parallel or in series. In this circuit, we combine the capacitors with 20 millifarads and 50 millifarads first because they are in parallel to one another. Since they are in parallel, the equivalent capacitance is just the sum of their capacitance values. This is represented by a single capacitor of 70 millifarads as shown.
In the next step, to continue to simplify the circuit, we observe two sets of capacitors in series. These can be combined by adding the reciprocals of the capacitors and taking the reciprocal of that number. For the first set, the total would be 21 millifarads. And the same process is followed for the second set of capacitors, which gives a total of 15 millifarads. These simplifications lead to the two equivalent capacitors now in parallel. So in the same way as before, we add their capacitance and get a total of 36 millifarads. All of these steps ultimately lead to two capacitors in series. So we calculate the total equivalent capacitance by adding the reciprocal of these two. This value ends up being 12 millifarads, and it represents the capacitance of the entire circuit.